In this lecture, we will explain the difference between univariate and bivariate distributions, explain the concept of correlation and the difference between positive and negative correlation, and draw scatter plots. Up until now, we've been working with univariate distributions. In this chapter, we start examining the relationship between two variables in what we call a bivariate distribution. Whereas before we described variables like height and weight as two separate variables, now we'll get paired data and show how the variables are related to each other. Here's an example of the paired data for percent of high school grads taking the SAT and the average SAT verbal score. Each dot represents one state. In the year from which these data are taken, approximately 28% of the high school graduates in the state of Colorado took the SAT, and for those Colorado kids, the average verbal score was a 543. Let's try plotting our own bivariate distribution using data on bird colonies. One of nature's patterns connects the percent of adult birds in a colony that returned from the previous year and the number of new adults that join the colony. We want to predict the number of new adults that can join a colony. I have the x-axis as percent returning and the y-axis as new adults. Now I need to set up my axes. When you do this in Excel, it'll happen very easily because Excel does nearly all of the work for you. But when you do it by hand, you have to do a little bit of thinking. The best way, in my opinion, to set these up is to look for the minimum values and the maximum values in each set of data. Remember, we have two sets of data. We have X and Y. So a minimum, let's see, 38, I believe is my minimum percent returning. My maximum, does anything go higher than that, 74? Yep, 81. 81 would be my maximum. So if I round down the 38 to say 35 and up the 81 to 85, it looks like I need to have a range of 50% if I don't start at the origin. So next thing you want to do is count the available lines that you have. So I'm going to just do that very quickly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay, so I've got 20 lines, and I want to be able to go at least 50%. So I've already rounded a little bit, but I probably should go by threes. Just to make sure that I have a complete set. So I'm going to put my little hash marks in there to indicate that we're not starting at 0. And I want to start here at 35. And then it's going to go 38, 41, 44. And I'm not marking every one just because I can't write that small. 47, 50, 53, 56, 59, 62, 65, 68, 71, 74, 77, 80, and 83, 86, 89. Alright, so I definitely have enough room. Let's do the same thing for the y-axis. My minimum value is 5, and my maximum value is 20. And this looks like it's going to be a perfect square. So my guess is I have 20 things going up as well. And if not, it'll be close enough that I can go by ones, starting even at 0, I think. Let's try. So if that's 0, then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and yep, 20. My suspicions were correct. Alright, now I just need to plot the actual values. So, my first dot is going to be at 74 and 5. So 74 would be along this line here, and 5 is this way, Find where they intersect and make a dot. Next one is 66 and 6. So 62, 65, so 66 is going to be just after this line, and 6 is one higher. So that looks good. 81 and 8. So 81, and then up 8. Next dot. I'm going to go ahead and pause this, put in the rest of the dots, and then restart the video, so it's going to look like they suddenly appear. Okay, so I have all of the dots now plotted. What you can see is that if I were to draw kind of a lasso around all of the dots, that I've got myself a pickle-ish looking thing that I could imagine a line going through that kind of averaged all the dots. We'll talk a lot about this line in this chapter, but it's called a best fit line. And in statistics, we go a little bit farther and end up calling it a least squares regression line. So you can see the lassoed up shape here is pointing down and to the right. That indicates that this is a negative relationship, which makes sense because as one variable, percent returning, increased, the number of new adults that came into the colony decreased. The scatter plot part of this is the actual dots. Okay, the actual dots on this grid represent the scatter plot. Then the title of the graph just needs to be something that's descriptive. In this case, I would say the relationship between the percent returning birds and new birds in colonies. Something along those lines. Alright, so what we've learned here is that for a bivariate distribution, to graph it, you're going to need an X and a Y axes, and those need to be paired data, meaning this is a single colony in which 74% of the adults returned and only 5 new adults in that same colony came in. Then you can set up your axes and plot the pairs of data as their individual dots. If you lasso up those dots, it'll give you an idea of the direction and eventually also the strength of that relationship.
Once you have a scatter plot, you can interpret it for 3 different things: form, direction, and strength. The appearance of the dot on your scatter plot shows the distribution's form. If the dots look like a circular shape, the distribution is referred to as radial. If you have dots that, when you draw a border around them, kind of looks like a pickle, then the distribution is called linear. Finally, some distributions, when lassoed up, aren't radial or linear and instead curve somehow. If the dots are linear, you can describe the relationship as either positive or negative. If the pickle goes up and to the right, the relationship is called positive. If it goes down and to the right, it is called negative. Positive relationships happen if the 2 variables have matching directions. For example, if a high x value is paired with a high y value, and low x's are paired with low y's, then the dots end up slanting up and to the right. If high values on one variable are paired with low values on the other variable, then the relationship is called negative. You can predict the direction of a relationship oftentimes just by using common sense. Let's try some. Age and strength among adolescents. I would anticipate higher values of age in the range of adolescents' ages to be paired with greater values of strength. As age increases, adolescents tend to get stronger. This describes a positive relationship. In the second example, we look at age and dependency on parents. In this case, I would expect for a teen's level of dependence on his or her parents to decrease as his or her age increases. Because the variables go in opposite directions, this relationship is likely negative. For C, the relationship is also likely negative, because as the number of days missed increases, the student's grades would likely decrease. For D, the relationship is likely positive, because as age increases, so would the size of a person's vocabulary. Size and spelling ability for college freshmen. Well, there shouldn't be any relationship between these two variables because a person's size has nothing to do with his or her ability to spell. Thus, I'd predict a correlation of 0 for these variables. G is kind of tricky. As age increases, the amount of time it takes to complete the race should decrease, making this a negative relationship. Finally, you can use a bivariate distribution to calculate the strength of a linear relationship by finding the Pearson correlation, symbolized by a lowercase italicized r. The more concentrated the dots in the linear form, the closer the value of r gets to plus or minus 1.00. If all of the dots appear on a single straight line, the correlation is called perfect and has a value of either positive or negative 1.00. The closer the value of r to 0, the weaker the relationship between the two variables, with the radial relationship having a value of 0.